What do Spring Boot, Helidon, Quarkus, or Micronaut apps have in common when it comes to protecting themselves against cyber threats and ensuring data protection? Java Security. Welcome everyone to Java Security Road to 21. I'm Ana Maria Mihalceanu, Java Java Developer Advocate at Oracle. And today we're going to see how Java Security evolved since JDK 17 so that you can safely build and deploy applications that use modern and strong algorithms and protocols. Java Security components continue to adapt to the dynamic security threat landscape.
Each change on the roadmap improves security in some way.
New root CA certificates. As the term Java Security is quite broad, let's first take a look at the Java Security components, as we are going to refer to those throughout this video. Java Security consists of language and runtime security functionality, along with a comprehensive set of APIs and implementations that cover many different areas. The higher level abstractions are built on top of lower layer concepts. The foundation of Java Security is based on cryptography. The cryptography components, Java Cryptography Architecture JCA, and Java Cryptography Extension JCE, enable you to encrypt and decrypt data in Java, manage keys, sign and authenticate messages, and much more. The PKI component contains APIs and implementations for validating and building certification paths or certificate chains, and storage of keys and certificates. Programs can access security services via the generic security service, Application Program Interface (GSS-API), and the JDK contains a GSS-API implementation of Kerberos. The Transport Layer Security component, also known as Java Secure Socket Extension (JSSE), contains APIs and implementations for TLS and DTLS. Sign jars allow you to apply a digital signature to a jar file in order to provide data integrity and authenticity. The Java Generic Security Service, Simple Authentication and Security Layer, Java Authentication and Authorization Service are a series of frameworks and APIs for authentication and authorization. The XML signature component contains an API and implementation for generating and validating XML signatures. Last but not least, I want to briefly touch on using the Security Manager. Or rather not using it, since it got deprecated for removal in JDK 17. The Security Manager was a feature originally designed as a sandbox for running potentially untrusted applets. Later, it got enhanced to support a fine-grained permission model, and as it was rarely used, it got deprecated for removal in JDK 17. Visit Road to 21 Upgrades video to get more insights on migration challenges posed by the deprecation of Security Manager, but for now, please keep in mind that if you use system.set Security Manager, you need to set the system property Java Security Manager to allow. A small set of tools can help you set security policies. Improvements on these tools are subject of JDK Tools Road to 21 video, so make sure to check out that one as well. A bit long, but necessary intro to this thrilling journey into the significant updates on Java Security. But now, let's get the ball rolling. The Java Security components continue to adapt to the dynamic security threat landscape by adding support for stronger algorithms and protocols, which you can see in this table. Other noteworthy details are that SHA-3 performance increased up to 2 times, and that the Sun GCE provided implementation of the ChaCha20 cipher algorithm now offers an optimized intrinsic for x86 64 and ARC64 platforms, yielding a significant improvement in performance. Larger key sizes provide stronger cryptographic protection, making it more difficult for attackers to compromise data. Moreover, Increased key sizes improve the resilience of encryption algorithms, hence ensuring confidentiality and integrity of data in transit or at rest. Cryptographic algorithms protect data and communication by using mathematical techniques to ensure confidentiality, integrity, and authenticity. Yet the tides of security threats increase with the advancement of technology. If large-scale quantum computers are ever built, all widely used digital signature schemes like DSA, RSA, ECDSA, and EDDSA have the potential to be broken. The IT industry has been working towards the goal of creating post-quantum cryptographic algorithms that are designed to be safe against an attack by either a quantum or classical computer. As these cryptographic algorithms progress and mature, they become standards and are gradually incorporated within Java security components. In consequence, one of the flagship security features of JDK 21 is HSS LMS signature verification implementation. The Layton-Micali signature system, LMS for short, and its multi-tree variant, the hierarchical signature system, HSS, are stateful hash-based signature schemes. It is believed that the security of hash functions will not be broken by the development of large-scale quantum computers. Thus, LMS signature is considered safe as it depends only on the security of the underlying hash functions. The new HSS LMS algorithm is intended to help applications having the following requirements. It is necessary to implement a digital signature scheme in the near future. The implementation will have a long lifetime. It would be cumbersome to migrate to a different digital signature scheme once the implementation has been deployed. To support such use cases, starting with JDK 21, you can use a key factory implementation available for the SAM provider to read an HSS LMS public key from its serialized format, for example, a certificate. Verify the validity of a signature that uses HSS LMS algorithm via signature implementation available for the SAN security provider. Above these cryptographic primitives are the modern protocols and standards. Let's check out what happened in that space too. Several performance-related improvements have been made to speed up and reduce the amount of memory used during a TLS handshake, like caching certificates decoded from TLS session tickets, avoid evaluating SSL algorithm constraints twice, caching the results of constraints checks. Speaking of TLS enhancements, did you know that the JDK implementation of TLS 1.2 uses a Diffie-Hellman key size of 1024 bits chosen by the server when a TLS DHE cipher suit is negotiated? Well, I agree with you. That's a complicated aspect to remember, but something that you for sure will remember is this. 1024-bit Diffie-Hellman keys are known to be weak and are no longer recommended. Using this default should be rare under normal circumstances. Moreover, most leading web browsers have deprecated the TLS DHE suites, so this should no longer be an issue. In consequence, in JDK 21, the default TLS Diffie-Hellman group size has been increased from 1024-bit to 2048-bit. This change does not affect TLS 1.3, as the minimum Diffie-Hellman group size for that protocol was already 2048 bits. So many cutting-edge improvements on the security algorithms make me confident that the Java platform will continue to provide a strong cryptographic foundation for our application development. Yet algorithms weaken and become vulnerable to attacks. Are you also worried about which algorithms are not safe to use? Then let's jump to the next section. Weak security algorithms are much like a flimsy lock. They provide a false sense of security that can easily be exploited. As these algorithms are the weak link in the security chain, Java limits or disables the usage of vulnerable algorithms to ensure a robust environment for developers and end users. In 2011, the National Institute of Standards and Technology formally deprecated SHA-1 usage. In 2013, NIST disallowed SHA-1 usage for digital signatures and declared that it should be phased out by 2030. In consequence, SHA-1 was disabled in TLS server certificates and in XML signatures. With JDK 18, jars signed with SHA-1 algorithms are disabled by default. To maintain compatibility with previously signed jars, this restriction does not apply to SHA-1 jars that have been timestamped before 1st of January 2019. However, this compatibility constraint is subject to change, so the best thing to do is to resign any SHA-1 jars with stronger algorithms. Speaking of weak algorithms, in order to make it harder to enable weak 3-DES cipher suits, these have been removed from the default enabled TLS cipher suits as of JDK 19. As 3-DES, RC4, and other algorithms got disabled, the TLS ECDH cipher suits got disabled in JDK 20 because they do not preserve forward secrecy and are rarely used in practice. TLS 1.0 and TLS 1.1 were disabled by default since April 2021, and as of JDK 20, DTLS 1.0 joined their party. The DTLS 1.0 protocol has various weaknesses and is no longer recommended. Applications should be using the more secure DTLS 1.2 protocol, which is also supported by JDK. However, if you encounter issues and you need to get your application working, you can still enable the DTLS 1.0 at your own risk in the Java Security Configuration file. There are multiple security properties defined in the Java Security Configuration file to control what algorithms are disabled in different areas. You can always add more algorithms to these security properties if you want to disable them, or you can remove an already disabled algorithm from the security property to make it available to your application again. Most of the algorithm disabling mechanism is configured via security properties in the Java security file. You can edit this file directly for a wide variety of configuration tweaks. There are two different kinds of properties listed there: those algorithms that are disabled and those that are defined as legacy. Disable means that this configuration restricts various functionality, whereas legacy means you really shouldn't use those algorithms because it's likely for them to be disabled in a future JDK release. As an example, TLS version 1 and TLS version 1.1 are disabled in TLS by adding those strings to the JDK TLS disabled algorithms security property in the Java security file. On the other hand, legacy algorithms are used as a last resort if there isn't any other choice available. For example, cert path RSA keys that are less than 1024 bits are disabled, but cert path RSA keys less than 2048 bits are also not very secure nowadays, so they are considered legacy. If tools such KeyTool or Jive Signer notice keys or certificates matching these various conditions, an appropriate warning will be displayed. In JDK 17, as specified by JDK Enhancement Proposal 411, the Security Manager was deprecated for removal. As part of that change, several Security Manager APIs were deprecated for removal, such as Access Control Context. The Subject to Us and Subject Get Subject APIs depend on the Security Manager related APIs, even though they do not require a Security Manager to be installed to use them. These APIs are important when you want to write secure applications that authorize subjects and perform sensitive operations based on their credentials. Thus, JDK Enhancement Proposal 411 outlined plans to provide replacement APIs that did not have dependencies on Security Manager APIs. These replacement APIs have been added to JDK 18. Subject Call Us is a replacement for Subject to Us, and Subject Current is a replacement for Subject Get Subject. The usage of these new replacement APIs is similar and simpler than the previous APIs. For example, using the old APIs to perform work as a particular subject required getting the access control context object first, while now you just have to invoke current method on the subject. If you're searching for a way to customize and retrieve the prioritized list of signature schemes used when negotiating a TLS or DTLS connection, I have good news for you. JDK 19 came with new APIs for customizing TLS and DTLS signature schemes. This is a follow-up enhancement to JDK Enhancement Proposal 332 on implementing version 1.3 of the Transport Layer Security Protocol. The new API helps applications customize the signature schemes for individual connections, thus providing granular control of the security properties rather than using the provider default signature schemes. We're going to stay a moment longer in the land of TLS and DTLS to talk about the API enhancements for customizing TLS and DTLS name groups. This change was introduced in JDK 20 and allows applications to customize and retrieve the prioritized list of name groups used to negotiate the key exchange mechanism in a TLS or DTLS connection. In the light of potential quantum attacks, Java developers and third-party security providers need a new encryption technique for securing symmetric keys using public key cryptography. So JDK 21 brings a new key encapsulation mechanism API. Similar to existing message digest, cipher, or signature, KEM is a cryptographic primitive now part of JDK 21. It allows the sender and the receiver to agree on a secret key using a key encapsulation message. A KEM consists of three functions. A key pair generation function that returns a key pair containing a public key and a private key. A key encapsulation function, called by the sender, that takes the receiver's public key and an encryption option. It returns the secret key and a key encapsulation message, also known as ciphertext. A key decapsulation function, called by the receiver, that takes as parameters the receiver's private key and the received encapsulation message in order to return the secret key. The new KEM API contains multiple new classes to ensure that all objects are immutable and thus thread safe. There are already KEM algorithms like RSA KEM and ECAS KEM, but it is said that KEM is the next generation of key agreement. The most common style to use a KEM is by having more overloaded methods that allow a user to provide algorithm-specific parameters or random sources when creating a new encapsulator or decapsulator. All classes involved are immutable. This means that you can create multiple independent encapsulators and decapsulators from the same KEM objects at the same time. For each encapsulator and decapsulator, you can also call their encapsulate and decapsulate methods at the same time to generate different keys, key encapsulation messages, and decapsulate them. As you observed, the Java Security API has undergone significant changes to strengthen the security of your Java applications. Additionally, there are a few native and OS-specific security features that allow you to take advantage of native credentials and other security information. So let's check those out. The OS native security features are typically available only for a certain operating system. For example, Windows stores keys and certificates for either the current user or the local machine, but you might need to access those. For this, you can use Sun MSC API provider to access native cryptographic libraries, certificate stores, and key containers on Windows. Yet, only certificates available to user accounts are listed when using Windows My or Windows Root. Windows My Local Machine and Windows Root Local Machine key store types were added in JDK 19 to provide access to keys and certificates stored on the Windows operating system that are available to all accounts. Furthermore, to avoid confusion, Windows My Current User and Windows Root Current User names have been introduced and mapped to Windows My and Windows Root respectively. All these changes are documented in the JDK Provider's Guide, and you can find it in this video's links. Some secret or private keys stay inside the OS and are not extractable to Java, and we have to call Windows native crypto API or CNG functions to make use of them. The same occurs on Unix-like systems with PKCS 11. Before JDK 21, only the user domain was considered when displaying the key store contents for the macOS keychain. Starting with JDK 21, the macOS keychain store implementation exposes certificates with proper trust in user domain, admin domain, or both. Furthermore, if there exists a deny entry for a particular purpose in a certificate's trust settings in any of both domains, the certificate will not be part of the macOS keychain store. Now that we touched the subject of OS certificate stores, let's look at the changes over JDK cacerts file. The cacerts key store, which is part of the JDK, is intended to contain a set of root certificates that can be used to establish trust in the certificate chains employed in various security protocols. The JDK root certificate CA key store no longer uses obsolete proprietary JKS format, as it was migrated to passwordless PKCS12 format. When using passwordless cacerts, you should be aware of: certificates are no longer encrypted, there is no MAC integrity check needed, and you don't need to change the password from the default, change it. But who's doing that anyway? However, if you decide to store sensitive information in cacerts, you should really create a password. When the root certificates from cacerts expire, they are removed. In JDK 18, this was the case of Google's Global Sign root certificate and IdenTrust root certificate. Yet in JDK 21, new root CA certificates have been added to the cacerts trust store, like the 4GTS root CA certificates. The evolution of the Java Security API has fostered deeper connection with tools and monitoring practices. Let's see how we can get valuable insights on certain security aspects. The JDK flag recorder captures events related to cryptographic operations, and in JDK 20, 2 more events were added. An event named JDK Initial Security Property, enabled by default, records details of initial security properties when loaded via the security class. Another event named JDK Security Provider Service records details about providers' GET service calls. This event is disabled by default, but you can enable it via JFR configuration files or standard JFR options. For debugging, you can always set java.security.debug or javax.net.debug.system properties to different values to print out or debug information in their respective area. It's worth mentioning that TLS has a new JSON-style output where you can look into details of every handshake message. When you need to manage and monitor remote Java applications, you can always rely on Java Management Extensions connections to facilitate that for you. So let's see how JMX connections have evolved from a security standpoint. Notably, as of JDK 20, the default JMX agent now sets an object input filter on the RMI connection to restrict the types that the server will deserialize. The default filter already covers any type that OpenMBeans and MXBeans might use. This enhancement effectively mitigates some deserialization vulnerabilities that could be exploited by malicious actors. The change should not affect normal usage of the MBeans in the JDK, but applications which register their own MBeans in the platform MBeans server may need to extend the serialization filter to support any additional types that their custom MBeans accept as parameters. You can find the serialization filter pattern in the management properties. So, if you need to pass additional Java types, you can override the default by running the following command. As we talked a lot about security enhancements, you should know that these are not randomly chosen. To make the evolution of the security features within the Java platform more transparent, let's hear about the Java Crypto roadmap from the expert, Sean Mullen.
The Java Crypto roadmap was created to inform the public about upcoming security changes to Oracle's JDK update releases. Many other JDK vendors also follow our lead and make the same changes. Each change on the roadmap improves security in some way. For example, we may restrict or disable a weak cryptographic algorithm or protocol. We may change a default to a stronger setting. We may add support for a stronger cryptographic algorithm or protocol, or we may improve tools to help you better diagnose security issues. Each change may have some compatibility risk. Therefore, each change typically includes testing instructions and details on how to revert the change. So another benefit of the roadmap is that you get advance notice of each change, usually a minimum of 3 to 6 months, and you're usually able to test the change before it takes effect to see if you may be impacted. With a few exceptions, changes are backported to all update releases. This is really important as your application can depend on the same level of security across all JDK versions. Since these are update releases, we try to reduce the compatibility risk of each change as much as possible. However, if your application encounters issues with any of the changes, you may need to re-enable disabled algorithms or revert defaults. But note that if you do so, you may be weakening your security posture. So please consult with your security experts before making any change.
With strengthened cryptographic algorithms, API enhancements, and improved secure protocols, you can boost your application's safety and safeguard sensitive data. By embracing Java security enhancements, you can build resilient applications that protect sensitive data, inspire trust to your users, and comply to security standards. And so we reach the end of the road to 21 for Java security features. If you enjoyed this video, please do me a favor and hit the like button. Also subscribe, ring the bell, and leave your feedback or questions in the comment section. Thank you for watching and stay tuned for the next video on the road to 21.
Congratulations on your game, Mr. Holmes. Exceptional. The awards ceremony will be tomorrow morning.